Welcome to part two of our lecture series from Wednesday, March 8th, where we kind of review our introduction to valence bond theory that was given on Monday. And I think a good place to start is by rehashing the definition of a bond according to valence bond theory. So we're starting with the definition here. By definition, a bond in valence bond theory is the result of half-full valence orbitals on different atoms overlapping to create a spin pair in that overlap region, where if the overlap is the result of some kind of head-on combination of orbitals, then we call this a sigma bond that is formed between atoms. So I think we looked at elemental hydrogen on Monday. I'm not sure, but this is a really great little illustrative example of what valence bond theory is saying. So let's say that I've got two hydrogen atoms. Each of them have electron configuration 1s1, meaning that these hydrogen atoms have a 1s orbital, and in each of these atoms' 1s orbitals, there is one unpaired electron. So according to valence bond theory, what makes H2, which Lewis would draw as H/H, or H singly bound to another hydrogen, is we would have our two hydrogen atoms close together, but not so close that their nuclei repel one another, but close enough so that we have a region of orbital overlap. And in this region of overlap, what were once unpaired electrons in each of the 1s orbitals on hydrogen now become a spin-paired electron duo in that overlap region. And it is this spin pairing in the overlap region that forms our bond. And in particular, because we had this head-on association of our orbitals, meaning they just kind of ran right into one another in order to overlap, this is a sigma bond. So here in the Lewis structure, what we called a single bond would now be called a sigma bond in valence bond theory. Now, that's not the whole story when it comes to valence bond theory, particularly when looking at covalent compounds that involve nonmetals with, well, basically anything that's not hydrogen. So let's talk about another key aspect of valence bond theory. So valence bond theory also states that atoms will hybridize their own valence orbitals to help facilitate bonding. So what on earth does that mean? So first of all, atoms will hybridize their valence orbitals. That is very bright. Let's do this one. Hybridize their valence orbitals, meaning that their outermost orbitals will blend or combine together. And how on earth does that facilitate bonding? Like, what does that even mean? So, there are actually two ways in which this hybridization process helps facilitate bonding. The first is that hybridization tends to increase the number of half-full orbitals on the atom, which means that there's more opportunity to bond. Right? Because if we've got a half-filled orbital, that can overlap with someone else's half-filled orbital and create a spin pair in that overlap region, and thus form a bond. But if we want like a more technical answer as to why bonding is facilitated when atomic orbitals hybridize, or when an atom combines its valence orbitals together, is simply something that comes from Aufbau. So hybridization let's not say results, let's say eliminates or removes the slight energy difference that is present between some valence s orbital and some valence p orbital. Because if you remember from Aufbau, which means fill low to high, filling up or building up principle, if I were to just draw a quick little diagram following Aufbau, I would start at hydrogen, which is my 1s. I could fill it with 1, 2, that'd put me at helium. And then I move right on up in energy, because I've now gone down a row, that is 2s. And if I move over from the s block to the p block, I'm filling the 2p orbital. But notice the 2p orbital itself is slightly higher energy than the 2s. After that, I fill my 3s, which is down another row, so that makes sense that it's higher energy. But if I were to go and fill my 3p, again, we see that there's this slight energy difference between the 3s and 3p, just like there was between the 2s and 2p, despite these orbitals having the same principal quantum number, n. So hybridization is going to remove this energy difference. It's going to eliminate that as something that we need to consider when it comes to like, where can I place energetically any kind of unpaired electron in some type of resulting overlap region. Okay, let's talk about hybridization. So by definition, what on earth is hybridization? So hybridization is the process where valence s, p, and sometimes even d orbitals combine to form new, what we call hybrid orbitals on the atom. So I think I showed you this already on Monday, but let's look at it again. Let's look at the result of some general S combining with some general P. So I'm just gonna like draw my PX side by side P. Well, here actually. How about I draw my P like this? And you know what? Let's actually draw my S first. So what if I've got my S orbital that is a valence orbital on some atom, and I add to that or combine it with some valence NP orbital. When I perform this combination of my regular atomic orbitals, I generate my hybrid orbital, which looks something like, as you'd imagine, a combination of the two. So let's see what that looks like. Here we go. So over here on the right is kind of like the result in 2 dimensions of what we would see here. Let's see here. We have to rotate this if that helps you. Here we go. I know that the text is upside down. Because when we combine here and here, we create a big blob, meaning down here we create a little nothing, smaller blob, if you will. And these are the shapes of the hybrid orbitals. So I can think about it as kind of this overall big greenish shape with the resulting small little orange lobe. That is my hybrid. So this is how I'm going to draw them. All right, so these are the hybrid orbitals. In the hybrid orbitals, as you can see here, the nucleus is within the minor lobe, meaning that the major lobe is what contains our electrons, typically. I mean, an orbital is still a probability density. We could, in theory, find our electron close to the nucleus. However, there's a larger space in this hybrid orbital that's surrounding the nucleus, so it's more likely to find an electron here than it is close to the nucleus. I digress. But in general, we are going to be looking at our hybrid orbitals as a result of combinations of atomic s and p orbitals when we look at valence bond theory. And again, the whole reason why hybridization happens is because it helps facilitate bonding from an energetic perspective, and it also makes more half-full orbitals, meaning we can form more bonds to potentially reach our stable or full valence electron configurations, which is what drives all of chemical bonding anyway, regardless of what kind of model you're using. So in our next video, we are going to look at a particular type of hybridization and how it occurs and why it's useful to know this hybridization, specifically by looking at sp3 hybridization. Now, sp3, sp2, and then later on Friday, as we'll see, sp hybridization. These are all things that are not going to go away in your chemistry career. You will see them pop back up when we talk about organic chemistry or when you move on to take organic chemistry, which I will certainly not be teaching. So yeah, it doesn't go away. So even though valence bond theory seems a little foreign because we're introducing that quantum mechanical nature of the electron back in, it will haunt you. So try to get comfortable here in the weird land of quantum mechanics. So see you in video 3.